Right, guys. Everybody who's supposed to be here is still here, except for Gary, who has to be in Lexington. All right, today, first we're gonna set up this is the only theoretical basis for pricing of derivative contracts. Now, I promise this is the only real math we're gonna do in this class, but when we were talking about futures or forwards, we kind of made an arbitrage argument that tied down the price. When it comes to derivatives in general, we're going to develop another arbitrage argument. That's going to basically say, if you can do that, you can price it. To do that, first, I'm going to write a generic equation for change in the price of some sort of assets. S can be a stock, where it has some sort of annual mean times delta t plus some volatility times something we're going to call delta z. Now mu, let's go annual drift, and sigma is annual volatility. Delta t is a very small time change unit. Technically speaking, mathematically we're doing this in continuous time, but I'm still treating it as if it's discrete. Delta z is something called Brownian increment. It is a random number, and that's equal to, let me use a different color for that. Let's see. It has a normal distribution with a mean of 0 and a standard deviation of square root of delta t. What this equation says, the change in the price of an asset is equal to basically a move on the trend. If this random part was 0, and this would be a constant number per unit of time. That means every delta t period, you would expect the stock to increase by that, by mu delta t. That's why we call it a drift. But for that, there is something random added. These are assets, and they're affected by news, and source of news are random. Something happens, price goes up and down, depending upon the nature of that move. Now, in general, generically, let the value of a derivative security or contract be denoted by C. It will be, among others, a function of time as well as the price of the underlying security. Which we denote by S. So if you have a call option on, let's say, Robinhood stock, the value of that is going to depend upon time and the value of the Robinhood stock itself. But that dependence is nonlinear. So C is going to be a function of S and T. Okay. Now, I want to be able to write expression for the change in the value of C. Which is equal to delta C. I don't know what that function is, but I know such a function exists. And without loss of too much generality, we're going to assume that that function is actually continuous. There's no jumps in the graph. That's what continuity means. Normally, I would write delta C. Normally, delta C can be written as the total derivative of C with respect to what you want to call S and T. So you would write it as delta C equals derivative of that function with respect to T. That's what kind of reverse 6 means. Take the derivative of the function, keeping everything else constant, plus derivative of that with respect to S times delta T plus sigma times or that would be it. If it wasn't for the random component. This is the standard, basic calculus. Don't worry about it. We're not going to do calculus here. But the trouble is, if you look at it, there is this random component. That means, in a sense, this function, technically speaking, is a function of stock price and the time, but the stock price itself also changes over time. Technically speaking, it's not continuous anywhere. So the standard calculus doesn't apply. But thankfully, that variation is of a bounded nature. It doesn't jump around too much, even though it does jump around quite a bit. Since the random component exists, standard calculus doesn't apply. But variation is of bounded nature. We have an equation that we can use to calculate